Now let's discuss piston pumps. Piston pumps are another form of positive displacement pump. The pistons are what provide the pumping volume, and we increase and decrease the volume by moving those pistons in the cylinders up and down in reciprocating motion. Right. In addition, we need to have valves, usually check valves or some other type of device that makes sure that the fluid is pulled in from the suction line and discharged from the outlet line. Now, the one thing about pumps is they're very well sealed. Fact is, piston cylinder arrangements are very tightly fit in terms of clearances, and as a result, you have a very high volumetric efficiency. We haven't talked about this yet, but essentially volumetric efficiency measures how much leakage there is, and so piston pumps provide sort of the tightest fit, and as a result, they also provide the highest volumetric efficiency and lowest leakage rate. In addition, because we've isolated the valves from the pumping mechanism, we can operate them at much higher speeds. So it turns out that these pumps are on the high range in terms of efficiency and speed, but there is a downside, and the downside is they're relatively complicated. And we'll see from the diagrams, particularly the cutaway ones, that there's a lot going on inside piston pumps as compared to vane and gear type pumps, which are far simpler. The way piston pumps are sort of subclassified is in terms of how the power input, how the shaft that's coming from the prime mover and the pistons themselves are oriented and how they move. So if we look at axial piston pumps, this means that the piston and the piston cylinder arrangements and the drive shaft are aligned axially or perpendicular to each other. And if you take a look here, you can see that where we have, here's a series of pistons, and here's the shaft continuing on through there. So they're aligned along with them. So the piston arrangement is axial to the drive shaft axis. Each of these pistons are housed inside a barrel, right? And in terms of this, the barrel is going to hold still as we rotate the drive shaft underneath. And you'll notice this surface right here. This is a cam surface. This is known as a swash plate. And on that plate, as it rotates around, it's going to move the pistons up and down, right? At this lower point, the piston is all the way extended up here. At this higher point, the piston is all the way retracted. As this rotates around once, it raises it and lowers it once. Attached to that is what's referred to as I said, a swash plate. This also provides us the valving, right? On one side, side A is our discharge side. On side B, this is our suction side. So this is when the piston is going to be retracting, pulling the fluid in. This is going to be when the piston is extending, pushing the fluid out. In addition, we have these piston shoes, right? This is essentially what attaches the piston to the swash plate, and this is what it rides on. And as you can see, as I mentioned, this is very complicated, right? I mean, the fact is we have a lot going on here, multiple valves, multiple pistons, and actually the piston volume is relatively small compared to the overall volume of the pump itself. So there are some limitations with pistons, but some main advantages as well. Another form of axial piston pump is the bent axis design. You can take a look here, you can see it. If we take a look, you can see that we have our drive axis coming in here, and we have our valve body and all the other parts to this all going to be separated at a bent axis. As this rotates around, you can see that these connecting rods, similar to the connecting rods in an automobile, are going to extend and retract the pistons that are in these housings, in these cylinders. right? So this rotates around, this moves the valves in and out, in and out. Similar to the swash plate, we have a valve plate. This allows the fluid to go in and out, making sure it connects to the fill port and the discharge port, and we make sure that the fluid moves in the right direction. Now, this can sometimes be modified if we can change the axes. Right? If you can adjust the axis, you can actually change the displacement of the pump. And in fact, if you were to align the axes so it was straight across, you would essentially have no flow at all. This is referred to as taking a pump off stroke. Right? This is another example of a piston style pump, which has very high pressure and very high operating, but this also gives us larger flows, right? So as we have slightly bigger pistons involved, because a lot of the valving and stuff like that is moved to this other portion of the pump. Now, the second way you can align the pistons is you can align them radially, meaning they are along the radius, right? So these extend and retract by the movement of this cam in here. This cam is going to move it up and down as it goes around. You can see the valving internally with check valves to pull the fluid out, push the fluid out, and you can see that it's going to be connected to the inlet port where it's sucked into this main section right here, and then pushed out of the outlet port. Now, this provides really good overall operation, great sealing in general, so you can really deal with some very high pressures, but you'll notice that the pistons and cylinder volume is a small portion of the overall volume. So we have a very small piston volume here, right? I mean, the fact is we're looking at something about that size that's going to be moving up and down and allow us to move fluid along, right? So it's a small volume, but it does allow us to have just about the highest pressure we're going to see. And in some cases, you'll see radial piston pumps up to as high as 10,000 PSI, but generally very low flows. Now, the other style of radial piston style pump actually involves rotating the whole cylinder arrangement. In the past one, we were just rotating the cam in the middle. This one, we're rotating the whole cylinder, right? And you can see those same shoes that we talked about earlier. They're riding on this ring. Right, this is what's referred to as a reaction ring. It's essentially a cam surface again. And one of the things about this is, much like we talked about with the vane pump, we can change the displacement by moving that ring back and forth. And that will allow us to adjust the stroke of the pistons themselves. Right. This again is a piston style pump, so it has high pressure, but as you can see, very complicated, a lot going on, and the piston volumes are relatively small. Now, there's a couple of unusual pumps that are used in special applications. One of them is a screw pump. If you take a look, this uses a screw mechanism, and essentially the fluid is pulled up through here and goes into the end of the screw, and as this rotates, it pushes the fluid along and out. They do need to be very tightly machined, so you have a very tight housing, so there's no leakage. You can accomplish this with a single screw, which you see here, but you also see 2 or 3 rotating screws all meshed together. Right? The idea is to trap the fluid in there and push it along. And one thing about it is, you notice it does not go along the axis, so it actually is a sliding contact, and the fluid is always coming in and always going out. So you get very smooth operation. The other thing about the contacts is the screws themselves never disengage or re-engage, so there's no kind of banging together. So this is a very quiet pump and with very smooth operation. It's also very expensive to manufacture. just take a look at that screw gear there, and you can see that would be very costly. Think about 2 or 3 of them. So you really only see these used when you want a very quiet operation, and one of the main places that they're used is actually in submarines. That's not to say that screw-style pumps aren't used in manufacturing. In fact, screw-style pumps are used in a lot of things like injection molded plastics and in other types of casting operations. But in terms of hydraulics, pretty much the only place you'll see it is when you want a very quiet operation. It's the only place that really justifies the added cost of a screw pump. The last of these special ones are lobe style pumps. Lobe style pumps are similar to external gear pumps. And if you take a look over here at the side, you can see it's similar. We have 2 gear-like elements meshed together, but they're not a drive and driven gear. Fact is, one of the big differences between these two is we have to drive both of them because, of course, there is no way for one of these lobed elements to push the other one. This is a positive displacement pump because we have good seals and it moves the fluid in a fixed amount around, and it works relatively well. It does have some issues in that in terms of the amount of seals, it's these sliding seals and sliding contact here, so we tend to have a limited amount of pressure they can withstand, so they tend to be low pressure pumps. The other thing about it is these are pretty big volumes, so these essentially have 3 big volumes that open and close. And as a result, if you were to look at the pressure of the fluid over time, you'd see that it goes up and down in a pulsating manner. So that's not something we normally want in hydraulics. We usually want things to be relatively smooth. So why would you use them? Well, the fact is, because the geometry is so large, you actually move a lot of fluid. And if you want a positive displacement pump that moves a lot of fluid and the actual smoothness of the output isn't all that important, lobe type pumps are a good one to use. Now, generally, we've seen these used in things like heat exchangers or any place where you want higher pressure, where you can't get away with a non-positive displacement pump. Okay, or I should say you can't get, and let's talk a little bit about non-positive displacement pumps. Now, the most common form of non-positive displacement pump is a centrifugal pump. It's a weird kind of, double negative there with the non-positive. The fact is, all it means is that when you rotate the pump, right, you go through one full rotation, you don't necessarily get the same amount of fluid every time. In general, what happens is the higher the resistance, the less fluid you get. Right? It still does move fluid from one point to the other, but it doesn't move it in a sealed chamber. As a result, a lot more backflow or a lot more internal leakage can occur. So let's show you how those work. So here's a impeller. Right? This is essentially the fluid is sucked in through the middle here, comes up, and then we see something that's similar to a vane style pump, but you'll notice the vanes themselves are curved, and the key issue here is you'll notice there's a lot of space between the end of the impeller and the actual sides or of the housing. As a result, fluid can easily bypass this. So what this relies on is it relies on acceleration. Fact is, the fluid comes in slowly as this spins around, right? It takes the fluid and accelerates it and essentially flings it out of this outlet. Now, if there's a great deal of resistance here, if there's some blockage or some, up the pipe resistance, we're going to see that the fluid flow is going to drop. There's going to be a significant amount of slippage in here. So these are very good when you want to move a lot of fluid, but there's not a lot of pressure involved. Fact is, anyone who's done any automotive work has probably experienced these. This is how we use water pumps, for example, in a car. We want to move a lot of water around to cool things down, but there's not a lot of resistance. It should be flowing through all the pipes, radiators, etc., with minimal back pressure. Another form of these non-positive displacement pumps are propeller pumps. They're pretty similar to a propeller on a boat except for the fact that they're inside a housing, as you can see over here. So as we spin this, the propeller runs and it pushes the fluid along. The propellers themselves don't actually touch the housing, so again, there's large spaces here, but these can be operated very quickly and can move a lot of fluid. The fact is, in a boat, for example, we move a huge amount of fluid to move a boat along. Now, if there's a lot of resistance, however, you're going to get a lot of slippage or leakage around these edges. So again, this is a non-positive displacement pump, and this has one complexity, and that is, how do you get the power into this, right? It is in the pipe itself. That requires you to use some type of elbow or other type of power transmission system. So propeller pumps are relatively rare, except for the fact that they're right embedded in the pipe itself, and if you need that type of close fitting for a given operation, you'll overcome this issue of the power. Another key thing about it is you tend to have relatively smooth operation because it is essentially ongoing. There's no opening and closing of any type of valve system. Now, if you have a pump and you want to increase or decrease the amount of flow, you can do it a number of different ways. One of them is to adjust the pump mechanism itself. This is known as a variable displacement pump, and essentially what you're doing is you're varying the volume of the pumping volume themselves. So for example, if you take a look down here, you can see in this setup right here, we have a cam ring, okay, that could be moved left or right. The pistons ride on the cam ring. In this case, it's centered. So even if this rotates, the valves themselves are, I shouldn't say the valves, the pistons themselves are not going to move up and down. They're at the same height all along. So you can get no fluid flow at all. If you move it over to the right, you've now maximized the flow, and you've noticed that the pistons are now going to ride on this cam ring up and down. If you were to move it all the way to the left, you'd actually be able to potentially reverse it depending on how the fluid valving is done. This can be done with our axial pistons, and this can be done with our radial pistons. This is a radial example. This is an axial example. This can also be done in an unbalanced vane type pump. Same basic idea, where the vanes are here and we could move the cam ring back and forth. So this is a common approach. Keep in mind, another way you could do it is you could put a flow control valve in. We'll talk about those. But what you're doing then is you're generating a lot of flow and you're only letting some of it through. In this case here, you only would be generating the flow you need, and that's one way of making the whole pumping system a little bit more efficient. Now, we want to make sure our pumps provide consistent performance, and that means we want it to have the same amount of volume each time it rotates. Well, it turns out that as pressures go up, right, you're going to tend to get more leakage and you're going to tend to get more friction. So we want to be able to essentially compensate for that. This can be done very simply in an unbalanced vane style pump and in the piston pumps with that same basic concept that we used before. Now what we've done is we have our cam ring here, right, and we have it biased by a spring. As the pressure goes up, right, this is going to push the cam ring over, and it's going to potentially generate more flow. But essentially what the flow is going to do is counteract any leakage and any frictional losses. Right? This again is designed to maintain consistent flow without spending more energy from your prime mover. Right. Much like all the other systems, you do want to make sure that there's a reef valve in this because pressure can build up. Actually, pressure can build up in this chamber and prevent this from working. So we want to make sure there's an internal relief valve in addition to the system relief valve. And in fact, nearly all of our systems are going to have multiple safety valves to prevent high levels of pressure from occurring. Now, when you're choosing a pump, you need to know the information up front. And you get that information from spec sheets or information sheets from pump manufacturers. All of these will have a set of specifications that tell you how the pump is going to operate. It's going to tell you things like maximum pressure. It's going to give you information about displacement. Of course, it's going to list other physical information like size and weight. Now, it turns out that some of the information, like displacement or like efficiency, is dependent upon other properties. So you need to represent that data in the form of graphs. So for example, we find that pump efficiency may go down as pressure goes up. There would be a graph that would show pump efficiency versus pressure, or versus flow rate, or versus temperature. And all those are represented well in the performance data that you'll find in the information sheet provided by manufacturing. In addition, it's very common to have installation information. How exactly should the pump be mounted? How should it be placed relative to the prime mover? Where are the mounting parts, let's say mounting holes, located? Overall size, shape, weight. All of that will potentially be in there. In addition, there usually is information about the operation. How often do things have to be maintained? How would you go about maintaining them? What are the replacement parts? All this can be found in the information sheets that pump manufacturers provide. There are some examples of this in your textbook, and there's a full manufacturing set of these on the course space for you to review as well. Now, to power a pump, you're going to need some form of prime mover. Prime mover is generally an electric motor, but it might be a gas engine. Potentially with a hand pump, it's a person, right? So the prime mover can come in a number of different forms. Generally, a prime mover is classified by its peak power. So a 10 horsepower motor or a 25 horsepower motor or something like that. That doesn't mean that it always puts out that power, but it means it's the maximum power that it does put out. So to determine what size we need to determine what our system's peak power is and sort of back calculate from there. To do that, you really need to find out what your system needs to do. So we start out with our actuators. Our actuators are going to lift a load or rotate requiring a certain torque. We need to work backwards, looking at the efficiency of our system, primarily the pump efficiency. Keep in mind, inefficiencies mean you have to put in more power. We definitely want to be concerned about temperature, pressure, and viscosity, because it's going to have a lot to do with how efficient the pump operates. And those all need to be taken into consideration as you're calculating your power needs. The standard method for doing this is to determine your power requirement in horsepower. And the conversion factor for horsepower is 33,000 foot-pounds of work per minute. So a 1 horsepower motor would be able to put out 33,000 foot-pounds of work per minute. In hydraulics, that's determined by the weight of the fluid, right? And we're looking at the weight of the fluid that moves past the object, or how much is pumped, and the pressure of the fluid. And in terms of the pressure, we can look at it in a bunch of different ways, but the simplest ways from a unit perspective is to look at it in terms of pressure head or fluid head. How high would the pressure push the water, or in our case, the oil, up? Right? So here's our general horsepower equation. We take our fluid flow in pounds per minute, we multiply our pressure in feet of head, and then we divide it by this conversion factor of 33,000 foot-pounds per minute to get it to horsepower. Now, these are not the usual units we use. In fact, we tend to take a look at fluid flow in gallons per minute, and pressure we tend to use PSI. And if we use those units instead, we can reduce the equation in terms of these basic units. And the more common formula for horsepower is our flow in gallons per minute multiplied by our pressure in PSI divided by 1714. Now, if you were to do this in metric, the fact is we would have flow in liters per minute, we'd have pressure in Pascal, and we'd have power over here in watts, right? And the one really nice thing about SI units is they're usually a one-to-one translation. The fact is you usually have a conversion factor of either 1 or in some case 1,000, depending on what units you use. Now keep in mind, every mechanical system has some level of inefficiency to it. Fact is, we tend to lose power in a variety of different forms. In our case, when we look at the horsepower required, we need to take that inefficiency into consideration. What essentially means is we need to have a bigger motor than what we need on the other end. The fact is some of that energy, some of that power coming from that motor is going to be lost in terms of inefficiencies. So there's two different inefficiencies we take into consideration in hydraulics. There's the inefficiency due to internal leakage. Now keep in mind, I'm not talking about fluid leaking out of the system or out of the system, say onto the floor. I'm talking about the internal leakage. And particularly when we're dealing with the pump, this is when we have fluid that's on the high pressure side leaking back to the low pressure side. Now, this is something we want to minimize in most cases, but keep in mind that leakage, one, is unavoidable. The fact is, no matter how close and precise you make a piston cylinder arrangement or a set of gears, you can't squeeze out absolutely every amount of fluid. The fact is, a small amount of fluid will be carried back to the inlet side regardless of how closely you manufacture it. The other thing about it is keep in mind that internal leakage does a number of things for us. It provides the lubrication. The fact is that oil leaks all around our device and it acts as a lubricator. It also cools that device off, right? Takes that heat from the friction away. And it also can be used in a number of other things. Sometimes we use it, for example, with vane type pumps, we use it to actually provide pressure to push the vanes up against the outside cam ring. So it's done a lot of different things that internal leakage is used for. So we don't want to have it to be zero, but we want to have it to be as small as possible. That internal leakage is measured by a property known as volumetric efficiency. Essentially, volumetric efficiency is comparing what we actually get to what would happen if we had no leakage at all. The other place where we lose energy is internal friction. We know there's internal friction in pumps because when pumps operate, they get warm. That heat that we're feeling is due to friction. The other thing we know we're losing energy is because of noise. Anytime you hear a mechanical device giving off noise, there's a certain amount of energy loss that is required to have that noise be created. This is measured by the mechanical efficiency, and essentially we're comparing the horsepowers to each other. Now, one thing about internal friction, you may say, oh, well, why don't we avoid that entirely? Well, the fact is we actually want that heat to warm up our oil. Our oil is generally going to be at an elevated temperature to room temperature, and that heat, it generally comes from the internal friction within a pump. So again, we want to minimize it, but we don't want it to be zero. In terms of our equations, we have our volumetric efficiency that uses the symbol V sub E. We take the actual pump flow rate, right, and the theoretical pump flow rate, divide those two, multiply it by 100 to get it in terms of percentage. In terms of this, keep in mind this is multiplied by 100%, so you're really multiplying it by 1. And the difference between the actual pump flow rate and the theoretical pump flow rate is the amount of internal leakage you have. In terms of our mechanical efficiency, we use M sub E, and we're going to take our theoretical horsepower and divide it by our actual horsepower. You notice this is flipped around. This is actual versus theoretical, and this is theoretical versus actual, and that's because of the way the inefficiencies work. In mechanical efficiency, we actually are going to need more horsepower than we theoretically would need because of friction. When we're dealing with flow, we're actually going to get less flow than we theoretically would get because of leakage. Now, the fact is the entire system efficiency or the overall pump efficiency is dependent on both of these, so we need to multiply them together. And we'll see that volumetric efficiency times mechanical efficiency will give us our overall efficiency, which uses the symbol O sub E. We are going to divide it by 100% again to get it in the right numbers. because we've multiplied this by 100 twice. But keep in mind, in each of these cases, this is 100%, 100%, 100%, and essentially we're multiplying by 1 or dividing by 1. And more than anything else, we're really just doing a unit conversion, going from a decimal to a percentage. Now, how do you use pump efficiency information? So, for example, you've gone to your info sheet and you find out that your pump is only 90% efficient at your peak pressure and flow. Well, you need to use that information, backtrack that information, and make sure that you upgrade your prime mover with that taken into consideration. So for example, if we take a look at the horsepower formula down here, we have our gallons per minute times PSI divided by 1714, but we're going to divide out our overall efficiency. Keep in mind our overall efficiency is going to be less than 1, so it's going to make the required prime mover power greater. Right, so say this was 90%, this is going to make the required prime mover power a little more than 10%. So without that efficiency, if we had calculated that we need, say, a 10 horsepower motor, with this efficiency, we probably would need an 11 or 12 horsepower motor. Right? If you prefer, I like to use whole numbers, so 1714 sticks in my mind. But if you prefer decimals, you can also do this exact same equation with 0.00538, which is just the reciprocal of 1,714. Now, the last thing we want to talk about in this section is about the inlet design. Right? The fact is the inlet or suction line of a pump has some important considerations. One thing to keep in mind, all of the fluid in the system is going to go through this inlet pump. So we want to make sure that it functions properly. Where we run into problems is because of the way the inlet pump works. The fact is the inlet pump runs from the reservoir to the pump inlet. We need to have a pressure difference to make fluid move. So the system reservoir, again, most of our system reservoirs are open to the environment. They're going to be at our environmental pressure or atmospheric pressure. So to get fluid to flow into the pump, we actually have to generate a vacuum. We have to actually decrease the pressure. And that happens when the pumping volume increases in size. It sucks the fluid in. Now, why this is a problem is it potentially can cause cavitation and or entrained air. Entrained air is essentially just air that gets sucked into the system. So let's talk a little bit about cavitation and why that occurs. So what is cavitation? Well, the easiest way to visualize this is to think about what happens when you open a carbonated beverage. Right? If you open, for example, a soda, before you open it, if you look at it, there doesn't appear to be any bubbles or any type of air trapped in there. Right? But as soon as you open it and you relieve the pressure, suddenly a whole thousands of bubbles come out. This is the CO2 that has been trapped in there that's providing the pressure on the system. And the fact is, as the pressure drops, the vapor pressure of the fluid is exceeded and it actually forms into these bubbles. You'll also notice that the bubbles actually stick to the sides of the container. Well, the same thing can happen if you have a significant amount of trapped vapor or entrapped air in your fluid. When you pull the fluid into the inlet or suction line, the drop in pressure can make these bubbles of gas form. Now, those bubbles of gas stick to the walls or the various components of your pump. And as the pump rotates around to the high pressure side, those bubbles are going to experience a dramatic increase in pressure. And what you can see is at first they're going to be reduced in size, but eventually they're going to collapse. And when those bubbles collapse, fluid is going to rush in to fill that void. This forms what's known as a microjet, and it can go at very high velocities. In fact, oftentimes the velocity is higher than the speed of sound and impact on the surface of the material. That impact is a very strong force that can break off chips and eventually erode the surface. has the potential to increase the part wear. It also is going to have a significant effect in terms of contamination, and the air bulbs themselves are going to not provide particularly good lubrication. So all this is a potential problem. Those collapsing bubbles can eventually erode the surface, cause a lot of damage to pump parts. They also can cause noisy operation, right? In fact, pumps with high levels of cavitation almost sound like they're full of rocks rattling around. And of course, those collapsing bubbles are going to cause pressure surges that potentially could, again, provide very uneven operation. So if you look at your fluid over time, you know, the pressure could surge up and down. That's something we generally want to avoid in our hydraulic systems. So the inlet line design is essential to make sure that this doesn't happen. And we'll talk more about that when we talk about reservoirs in general. As always, if you have questions on any part of this presentation, don't hesitate to get in touch with me. There's also a great deal of information available on the course base to show you how pumps function, additional details about cavitation, which definitely make sure you review.